we're going to talk about the CO2 molecule. CO2 molecule. Okay, CO2 molecule. It's called CO2 because it contains a carbon, and it's called O2 because it contains 2 oxygens, like that. And it's a molecule because it has more than one atom in a stable configuration. Okay, it's the actual arrangement of the 3 components in this linear arrangement, and of course, if you were to kind of get your head around what you're actually looking at, the carbon. The carbon has 6 protons. So let's represent 6 protons here. 1, 2, 3, 4, 5, 6. It has 6 neutrons. 1, 2, 3, 4, 5, 6. And it has 6 electrons, which, if on that scale, would be somewhere, I don't know, several hundred meters away, kind of fuzzing around in the far distance. Okay, that's your carbon. Then you have your oxygen, which has got 8 protons. Which one's proton? Oh, it's proton. So 1, 2, 3, 4, 5, 6, 7, 8, and 8 neutrons. 1, 2, 3, 4, 5, 6, 7, 8 in the nucleus, and similarly 8 electrons, which are far away out there. Now, what is really interesting about the CO2 molecule is the way that it interacts with infrared photons. Now, if we were to say that the CO2 molecule reacts to infrared photons, we would actually be sort of more inaccurate than we would be accurate. Because if this was hypothetically was the infrared electromagnetic spectrum, then there's only 2 little places on that spectrum where the infrared photon, where the CO2 molecule actually interacts with infrared photons. Okay, and they are, and so let's say, for example, that we're going from 0.78 up to 1 to 820, and this is, what is that? That's micrometers. Micrometers, represented by the mu symbol. Okay, so that's the IR spectrum. All right, from 0.78 microns to 12,820 microns. Then there are 2 locations on that. So that's 0.78 and that's 12,000. So the first one is actually right over here, and that's at 4.26 microns. Okay, and then there's another point around about halfway. It's about 667, so it's around about here. That's at 667 microns, and it's at these 2 locations on the infrared spectrum that CO2 molecules actually start getting excited and actually do something. All right, any other bit of infrared photon striking that CO2 molecule it's just going to pass straight through it. Nothing's going to happen. However, if you have an infrared photon with 6.26 micron mu, right, let's go back to this. The symbol mu, all right, is micro. All righty, so 10 to the negative 12. All right, so 0.78 micrometers, 12,820 micrometers, 4.26 micrometers, 667 micrometers. Okay? Now, if the CO2 molecule is exposed to a photon of 4.26 micrometers, then you're going to start to see asymmetric stretching. Okay, asymmetric stretching. What that means is you're going to see your carbon is going to start wobbling that way, and it's going to start wobbling all that way, And in so doing, what you're going to end up with is asymmetric stretching. So let's put it this way. Asymmetric stretching would have the carbon come over here, and then a little bit later, the carbon would wobble and it would come over here, right? And in so doing, what's happening is as the carbon basically shuttles in between, okay, the two oxygen atoms, you change the dipole moment. Now, if you change the dipole moment by bringing in your infrared photon, and let's represent it like this. Okay, so that's an IR photon. IR photon, boom, hits the CO2 molecule. IR photon with a wavelength of 4.26 micrometers hits the CO2 molecule. It's going to start vibrating by shifting that carbon backwards and forwards. That's called asymmetric stretching. It's a type of vibration called asymmetric stretching. And as the carbon moves backwards and forwards between these oxygens, it's going to change the dipole moment. What does that mean? What that means basically is that the configuration of electric charge on the atom changes, all right? Now, hypothetically, if you had symmetric stretching, which is a way that CO2 molecules vibrate, they vibrate with symmetric, asymmetric, and also with bending, we'll come to that, right? But the symmetric stretching is not IR active, okay? So let's have this term, IR active. Okay, so asymmetric stretching is IR active, which means it is activated by the presence of infrared photons. Okay, and the reason why symmetrical stretching is not IR active is because it doesn't change the dipole moment, right? So what that means is if you had symmetrical stretching, and imagine the C stayed in the same place, but these oxygens went boop, 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 evenly, that is not changing the overall electric charge configuration within the molecule. Therefore, you're not changing the dipole moment. And it's the changing the dipole moment, which is what this thing does. If it doesn't change the dipole moment, the molecule is not responsive to infrared photons. Okay, now, let's say, for example, over here, we've got another infrared photon. This one is 667, right? Then what you're going to see is you're going to see bending. And for bending, we need to go to another sheet of paper. So let's go and build my little CO2 molecule again. So what happens when we get our, okay, so this is a 667 microns IR photon, okay, and what we're going to do is we're going to see it's going to IR active, okay, for bending, okay, bending being a type of vibration, okay, exists as bending, right, and stretching. And I think there's a third, I can't remember at the moment. So what happens with bending? Now bending actually takes place on two planes. So imagine that here's one plane where we're looking at the molecule from the side, and imagine in this plane, we're looking at the molecule from the top, okay, hypothetically. So what we've got going on in IR, in bending, is you're going to see the carbon is going to start kind of moving like this. So you're going to start to see, I don't know how to describe this, but basically the wings are going to start, think of it like a bird, right? Here's a bird flying at you, right? And here's its wings, and here's its wings when they're in the down flap. Okay, there's its feet, whatever. Yep, that's actually a pretty good bird, I think. That's fucked it completely. Anyway, so it's like if you're looking at the molecule, it's kind of boop, 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 bending like that. Now it can bend in the plane of the bird flapping its wings up and down. It can also bend in the plane of the bird bringing its wings forward and back. All right, so you've got these two planes of IR, of bending, which is a type of vibration, which is a motion that is set in place with the CO2 molecule. All right, now, so let's not forget that the molecules are not just sitting there doing nothing. The molecules are actually like, pew, right, flying around the place at hundreds of kilometers a second, right? And so let's say, for example, the green is the CO2, right? When let's say, well, then you're going to have hundreds of these ones. Okay, so the dot is N2, right? Let's say that this is O2, okay, and then this is CO2, right? So basically all of these, now obviously 78% of everything that's going on here are N2, around 21% is O2, and the CO2 is tiny fragment, 4 parts in 10,000 in the atmosphere, right? Now, what you've got after being exposed to the infrared radiation in these two frequencies where you've energized the molecule is that this little guy is zooming around the place. And let's say, for example, that we have a close-up, right, of this highly energized, okay, CO2 molecule, highly energized CO2 molecule, bounces into the old N2, just floating around doing its business, okay? When those two collide, one thing that can happen is that the highly energized CO2 molecule loses its energy, drops down in its energetic phase, but in so doing, actually fucking boom, fires the N2, adds its translational energy, all right? Translational energy is the movement of the particle, movement through space. Okay, so over here we've got the infrared photons, right, activating the CO2 molecule, although it only occurs in a very small proportion of the atmosphere. But in these natural collisions that are happening all the time as these things are flying around bouncing off each other, it's periodically giving up some of its vibrational energy and it's turning it into translational energy, which means that the molecule it bounces into now travels faster through space, and it's the average speed, right, of the air molecules, right, equals the heat of the air, right? So the average speed of the air molecules is equal to the temperature, the temp of the air. So if you just keep having these CO2 molecules picking up these infrared photons, like increasing their vibrational energy and then dumping that vibrational energy through collisions into an oxygen mainly, right? Then they're going to basically increase the translational energy, the speed, the velocity of these other molecules, and in so doing, heat the atmosphere.